Good afternoon and welcome to the final session for Discovery Day 2018. My name is Peter Abbott and I am the Principal Mineral Industry Analyst at the Department for Energy and Mining. As a former member of the Geological Survey, I'm delighted to chair this session on GSA connections and commodities. The Geological Survey worked together with many collaborators locally, nationally and across the globe to share ideas and new perspectives in geoscience. And today we've got a very special treat for you. We have a presentation from the other side of the world, and our first presentation is a keynote address from Dr. Sally Pehrsson. Sally is a research scientist and program lead at the Geological Survey of Canada, based in Ottawa. Sally is a structural geologist and a true world expert on the link between supercontinent cycles and mineral deposit formation. This presentation that we're about to play was recorded for us by Sally earlier in the week and is her contribution to our Discovery Day in recognition of the many geological connections between Australia and Canada.
Good morning, everyone. I'd like to start by thanking Anthony for the invitation to vicariously speak to you all this morning. It is a real pleasure to present at Discovery Day and think about Australia and Canada, especially because I'm presently looking out on a flurry of snowflakes and wishing I could be there in person. So you might be wondering how it is that a geologist who's worked all her life mapping in Canada's north would wind up thinking about Australian ore deposits. Well, the answer is simple. I blame these two guys. On the left, Josiah Flintabity Floniton, the hero of a 1905 sci-fi pulp book, The Sunless City, that was in the back pocket of the prospector who found an outcropping VMS deposit on the shore of a Manitoba lake. He named the deposit Flin Flon for short, and while I was running a program there, I met David Houston, the guy on the right, and we started talking about the intriguing correlations between North Australia Craton and Flin Flon VMS. What I'd like to talk to you about today is the link between ore deposits and supercontinents. The mineral deposits that we're going to discuss are formed and preserved through a complex interplay of subsurface and surface processes that are profoundly affected by long-term secular change in Earth's atmosphere and hydrosphere, and its more episodic changes, which occur at both short frequencies, such as magnetic reversals or Milankovitch cycles, and long frequencies, such as the last item here, supercontinent cycles. For this latter one, the link between the ore deposit record, its heterogeneity, and the equally heterogeneous supercontinent cycle is well established. From the early work of Meyer to more recent papers, as an example shown here, of David Groves and Frank Behrlein, this has a significant potential to be used as a predictive exploration tool. On the right here, I show the supercontinent cycle in a diagram from Damien Nance. It encompasses the assembly, stable tenure, and breakup of a supercontinent, and has happened multiple times through Earth history, as Dwight Bradley's examples show here. But crucially, it's happened in two complete cycles, enough to establish its validity, twice in the Proterozoic, and our new compilation of metamorphism through Earth history, shown here in blue, clearly tightly establishes a cycle of about 600 million years duration for the Precambrian. So what about Australia and Canada's links in this cycle? Well, since the hallmark paper of Bell and Jefferson 30 years ago, many researchers have proposed reconstructions that marry Australia and Canada. One of the earliest is the well-known sweat hypothesis by Ian Dalziel. More recent work by Giles and Betts is well known, and of course for Rodinia, there is the Lee et al. Major Rodinia project. Intriguingly, more recent reconstructions, such as this lovely one by Andrew Meredith here, South Australia, has started to be much more robust in that they use animations to guide realistic plate motions, including realistic plate speeds. Earlier than Rodinia time, we've had several decades as well of reconstruction, including the early work by Gaojian Zhao and more recent work of my colleague David Evans and Bruce and myself, and one I'm going to show you shortly. But the fun part is that people are even trying to work at them even earlier. This is more speculative and presently tantalizingly very fuzzy. These involve pieces of Australia such as Ilgarn and Gawler. For the former, we have Superia. This is a supercraton proposed by Wouter Bleecker a number of years ago. And by supercraton, we mean a component of cratonic pieces that came together in an assembly that is probably about the size of a modern-day continent, and certainly not the scale of true supercontinents such as Pangaea. But the linkages are really clear. And so for Superia, it came together by about 2.6, and it's crucially pieced together using the Saskatchewan 2.4 billion year old dike swarms shown here with Hearn and other cratonic pieces in Superior, but also sedimentological links. So all of these pieces have examples of a 2.5 rift sequence, the Huronian supergroup, that crucially in its younger parts has glacial diamictites, and all of the pieces shown pieced here do have that. Very interestingly, recently Sergei Pizgareski and his colleagues have demonstrated that the Ilgarn probably was part of this association. They dated the 2.4 Arayina dikes of the Ilgarn craton, one that's coeval to the Saskatchewan swarm, and their paleomagnetic data allows placing Ilgarn within the Superior arrangement. So this is really exciting new work that has the potential to be very predictive. The other supercraton that we're going to wave our arms a little bit about, so to speak, is Nunavusha, and this is one that I've proposed based on a double barcode of the McCoy and Arrowsmith orogenies. Shown here on this paleographic representation of the modern day world are all the cratons that were involved in Nunavusha, shown in red. Many of these are very small fragments that have been reworked in other origins, but crucially the largest ones, such as Gawler, India, Darwar, North China, and the Ray craton of Arctic Canada, have this paired association between early accretionary McCoy orogeny and younger, more continental, moderate pressure, high temperature Arrowsmith orogeny. We'll come back to this later. So what I'd like to show you now is a series of snapshots and then an animation from our current continuous plate model. And this is going to focus on the time period evolving from Nuna to Rodinia. And it's important to note that once we discuss these metallogenic implications, what we're showing is underpinned by major global databases of geodynamic blocks, paleomagnetism, metamorphism, and crucially including ore deposits that can form in geodynamically distinct settings. So our first time snapshot is between 2.2 and 1.95 GA, and all of them are going to have a similar look and feel here in that we're going to have plutonism, volcanism, and peaks of metamorphism plotting as smaller scale dots in the exact location on the plates where they formed in real life through ArcGIS, and then also the mineral deposits shown in the variety of different colors and symbols shown along the bottom here. As you can quickly see, the very first amalgamation for Nuna is in the Amazonia, West Africa sector, and this is host to this rash of yellow triangles for lode gold, which is the Birimian Gold District. If the rest of the diagram really looks very unfamiliar, that's because Nuna hadn't come together yet. Laurentia is in pieces, shown here in the north, as is Baltica, upside down and on their heads because they formed in the northern hemisphere in that orientation at that time, and again Australia in a series of pieces. The second main accretionary phase is where the bulk of the major mineralization for Nuna happens, between 194 and 188. And as you can see, the Manicaean Ocean between the different parts of Laurentia has started to close, and there's a formation of a whole series of volcanic interoceanic to prairie-cratonic arcs that host the major VMS district at this time, the Trans-Hudson, Flin Flon, Otjipumpu, and Skellefteå districts in Baltica. Over 85 major VMS deposits globally totaling 1,520 million tons of ore. At the same time, on the Superior side and also in Baltica, we have the major nickel deposits at this time that are actually broadly syntectonic with respect to this ocean closure. And these include the Thompson, Raglan, and Pechanga districts that total over 250 million tons of ore. After about 1.87, Manicaean has closed, and so now we see a more familiar closed Laurentia here, again upside down and on its head. North Australia craton has largely come together, although pieces are still going to come in. And here we see the whale tail, if you will, of Mawson and South Australia and the Curnamona districts. From a mineralization perspective, the terminal closure of the interior ocean resulted in a whole series of major gold deposits, Meadowbank, New Britannia, Homestake, Tanami in Australia, and importantly, a series of, in the successor arcs and late arcs, a clustering of iron oxide-related magmatism in the Great Karuna and Great Bear districts. This stepping outward to a peripheral orogenic phase overlaps with the major final assembly of Nuna. Here we show Australia having finally arrived in Laurenția's northwestern sector, and this accretion focused in this sector contemporaneous with the long-lived southwest US, Baltica, Amazonia, Andean-style margin. Metallogenically, there's a range of IOCG and intrusion-related deposits at this time, shown in the red boxes, along the interior, but also the continental arc magmatism, showing in this rash of dots along the outer margin. At the same time, there was a series of ultrapotassic volcanosedimentary sequences erupted into the interior of Nuna, shown in these different yellow stars, and these moved metals from the metasomatized mantle lithosphere up into the upper crust. So what can we take away from this data? Well, ultimately, if we put together a series of different time slices all together, the ones I've showed you and others, we find there's a distinct pattern of association between ore deposit clans and specific stages of the supercontinent cycle. VMS, lode gold, and nickel deposits are in association with the early interior orogenesis related to the major Manicaean and other ocean closing. This is the characteristic environments of the North Australia Craton and Trans-Hudson. These deposits notably decline during the peripheral orogenesis phase, even though arc systems are continuing to accrete. But there is an association with unconformity uranium deposits and other types of sediment-related deposits such as clastic lead zinc, MVTs, and sediment-hosted copper. What is the geodynamic implication for this? Well, I'd like to suggest that there's an influence of supercontinent assembly style on mineral endowment. And to show you this, I'm going to use VMS as an example. This compilation of VMS deposits through time, which we did with Dave Houston, illustrates that during Nuna's early aggregation phase, we have a major peak of bimodal mafic ore deposits. At the same time, or in the same vein, subsequently, during the Phanerozoic, when the Iapetus interior ocean closed, we have a major peak in bimodal mafic deposits again. These peaks that are showing an association to arterial orogenesis, we suggest, is favorable to mineralization because of the preponderance of repeating subduction, formation of the paracratomic arcs on microcontinents from the preceding ocean open that are proximal to margins that they will quickly abduct upon. In contrast, when we highlight the peripheral phase that I've just elaborated for you, Nuna has almost no VMS mineralization. And then when we compare to Rodinia, whose predominant geometry was inherited from Nuna and is largely an exterior ocean closing system, again, almost no VMS. We would argue that this is because the differing age and oceanic lithosphere that is consumed during the collision governs what type of mineralization and preservation can happen. The old oceanic lithosphere, with its advancing accretion, lack of back arcs, and delay and related structural preparation, delayed long time periods for arc accretion, dooms the mineralization. And as you can see here, there's a stark contrast between Rodinia and the other major supercontinents of the world. Shown here, relative age on the x-axis, on the y-axis, the difference in time between formation on the seafloor of the host to a VMS deposit and its accretion into the origin. For Rodinia, we have just deposits because it has so few. For the other supercontinents, we have entire district averages because there are so many. And what's clearly evident is that a short time period on the order of 30 to 20 million years or less before oceanic plates achieve neutral buoyancy is the sweet spot for arc abduction and VMS preservation, whereas Rodinia, which took a long time to have its deposits come in, the oceanic plate that those are riding on has already started to subduct and doomed large-scale preservation. So I just want to run for you now, very briefly, a paleoplates model that we've done that's our most recent work showing where parts of Australia's cratonic sequences were relative to Laurenția, and we'll see if this thing runs properly. We're going to cross our fingers. There we go. So this model is from the Nuna to Rodinia transition, and you can see by 1600, North Australia craton coming in to the northwestern margin sector, and Mawson and Gawler here are showing just off of the Wernicke Mountains in Laurentia. So we've shown this orientation with Laurentia update from the North Pole looking towards southward. All of the different magmatism and deposits were coming off and on, just as we would have previously shown. And so I'll briefly run that again for you. Give you another view of it. Here comes Australia in, colliding, magmatism setting up on its peripheral long-lived arc system on the southeastern US margin through here with Yavapai Mazatzal, and North Australia craton and South Australia Mawson coming in adjacent to northwestern Laurentia and then ultimately coming off again. So what is the effect of this? Well, this crucial time period, we would suggest that there is a sediment-hosted deposit trinity that relates to this late phase of fairly soft external collision, very transitory, between pieces of Australia and West Laurentia. In Australia, this is known as the Eisen orogeny, and in northern Canada, it's known as the Racklin forward orogeny. These overlap at the same time, right around 1.6, and at the same time, we have a host of different sediment and possibly evaporative brine-linked ore deposits, such as Mississippi Valley type deposits shown in blue, green sediment-hosted copper, and unconformity uranium shown in orange. Also, but not plotted here, are hydrocarbon deposits that are known in the younger parts of some of the basins, the Roper and Elu Basin in Arctic Canada. So clearly we have a major series of mineralization being driven by this, and it's crucial to note for reference the scale on which these deposits and fluids can be driven by these collisions. The Racklin front is actually 1,800 kilometers inboard of the margin. So now after this, we have a time period of attempted, repeated breakup. Nuna came together by 1.6, roughly speaking, and then very shortly afterward, and even just prior to that, a whole series of rift events and lip events came through the different pieces of Nuna. Ultimately, the Australia, Siberia, and Laurentia triple junction focused this extension and allowed Australia to rift away. But initially, it occurred through many different parts of Nuna. At 1750, we have the formation of major volcanosedimentary rift basins and Rapakivi granites in a whole series of basins, including the Espinajo and the Wharton in Canada. And in the Canadian examples, they actually host epithermal low sulfidation gold deposits, the Mallory, and these are examples of the Chalcedony veins and fluorite in their mineralization. At this time, when Australia did finally succeed in breaking away, we have the formation of the world famous Sullivan lead zinc district on the Western Canada margin, and this is host to 160 million tons of ore. This failed arm, though, crucially, between Siberia and Laurentia, preserved the main geometry through the boring billion into the Neoproterozoic and was the main architect by which Rodinia inherited Nuna's geometry. The younger time period that's so important metallogenically, where there was the preliminary attempted breakup and then successful, well, that's got to be the Olympic Dam time. And as this audience knows way more about Olympic Dam than I do, I'm just going to highlight where it's sitting in our reconstruction, but also that crucially there are equivalents to the Olympic Dam system on the adjacent cratons that were involved in Nuna at this time. The 1.59 Wernicke breccias are well known in Yukon, and this is a photograph of Slab Mountain in the Yukon that is host to the Wernicke breccia, where pieces of the accreted slab volcanics, as Derek Thorkelson has called them, are present within the breccias, as well as preserved pieces of different parts of the Wernicke group that actually have Racklin forward orogeny on them. The mineralization here is more small scale, but it is there and hasn't been widely explored. And even more intriguing, it's recently been reported that Yangtze Craton has mineralization and veining of this age and the potential for IOCG Olympic Dam type mineralization. One of the happy accidents of the ultimate successful rifting of Australia off of Northwest Laurentia is the terrain transfer of the Georgetown Inlier with the North Australia Craton. It's apparently a piece of the Yukon that has come away and gone east and gone outward with Australia. So last but not least, in this transitional time period between Nuna and Rodinia, what is the metallogenic effect of the long-lived peripheral subduction? Well, as I think you can see here, it's very clearly the localization of rare earth deposits and prospects associated with carbonatites and alkaline magmatism in a long zone about 300 kilometers inboard of the subduction system, effectively in far-field back arc settings that are locally post-tectonic to the regional structures. And my immediate question is, does this continue into South Australia? Paleogeographically, one might think. So I'm now going to just very, very briefly touch on the older supercraton connections and then leave you with a final concluding thought. As I mentioned earlier, Superia is beginning to be reconstructed, and this is really exciting because a colleague of mine, Rolly Riddler, in 1971 drew attention to the similarities between Ilgarn, Superior, and Hearn cratons that all may have been part of Superia. All have a distinctively rapid style of greenstone formation and assembly, and ensuing efficient preservation of world-class volcanic-hosted massive sulfide and lode gold districts in long linear belts, very distinctively. And I would suggest this is their metallogenic inheritance. The part that we think it will be possible to actually potentially explore more for is lode gold. The world-class Meliodine deposit that is going into production now on the shore of Hudson Bay, we have recently been finding indications that from rhenium osmium dating that its early gold and sulfides are Arrowsmith age. So finally, I'd like to leave you with one message. Thank you for your attention, and please remember that there are associations of deposit types with specific phases of supercontinent assembly or types of supercratons that potentially can be used predictively, exploring using lessons from Australia and Canada's long history of their involvement in Precambrian links. Thank you.